now we're going to add the little degree symbol to deltaG. By definition, standard free energy change, deltaG naught, is the free energy change for a process occurring with all the reactants and all the products in their standard states. For example, the standard free energy change for the Haber process at 25 degrees Celsius is negative 33.3 kilojoules per mole of reaction. That means that 33.3 kilojoules of free energy is released when 1 mole of nitrogen gas at 1 atmosphere reacts with 3 moles of hydrogen gas at 1 atmosphere to produce 2 moles of gaseous ammonia at 1 atmosphere. Free energy changes cannot be measured directly, but there are at least 3 different methods we can use to calculate it from the other measured quantities. The first method was the one introduced in the last video and uses the free energy equation that we derived from the definition of Gibbs free energy at constant temperature. Since standard conditions means that the temperature is 25 degrees Celsius or 298 Kelvin, we have everything we need to substitute, as long as we pay attention to units. So deltaG naught equals negative 393,500 joules per mole of reaction minus 298 Kelvin times 3.05 joules per Kelvin per mole of reaction, giving us a total of about negative 395 kilojoules per mole of reaction. A second method used to calculate deltaG under standard conditions employs the manipulation of systems of equations like we did for enthalpy change using Hess's law. This works because, like enthalpy, free energy is a state function. So if we can get 2 or more chemical equations to add up to the process we're studying, then the free energy changes of those equations will add up to the free energy change of the process we're studying. For example, this chemical reaction is the oxidation of carbon monoxide to form carbon dioxide. Some other thermochemical equations and their standard free energy changes are given. So how could we manipulate reaction 1 and reaction 2 so that they sum to the reaction we're considering? Well, to get 2 carbon monoxide molecules on the left, we'll have to flip the first reaction. This also changes the sign of deltaG 1. Now to get 2 carbon dioxide molecules on the right side, we'll have to double the second reaction. This means we'll double deltaG 2 as well. Now the sum of these 2 reactions is the one we're looking for. So the sum of their deltaGs will give us the deltaG we're looking for, which is a total of negative 514 kilojoules per mole of reaction. A third method for calculating standard free energy changes for a reaction uses standard free energies of formation in much the same way that you used standard enthalpies of formation before. Similarly to how we defined the enthalpies before, we'll have standard free energy of formation for a substance is the change in free energy that occurs when the formation of 1 mole of that substance from its component elements, with all the reactants and all the products in their standard states. For example, the standard free energy of formation for glucose is the standard free energy change when 6 moles of carbon in its standard state, solid, reacts with 6 moles of hydrogen in its standard state, gas, and 3 moles of oxygen in its standard state, gas, to produce 1 mole of glucose in its standard state, solid. As with using standard enthalpies of formation, the standard free energy change can be calculated by subtracting the sum of the free energies of formation of the reactants from the sum of the free energies of formation of the products. The standard free energies of formation are tabulated in your textbook's appendix. You won't need to look up the formation free energies for elements in their standard states because those are all 0, just like with enthalpies of formation. Here's an example using the combustion of methanol gas, and the free energies of formation given. Notice the free energy of formation for oxygen gas is 0, because it's in its standard state. We'll sum all the products, multiplying by their coefficients, and we'll subtract the sum of all the reactants, multiplying by their coefficients. We get a grand total of about negative 1.4 megajoules per mole of reaction. The negative sign means that this is thermodynamically favored. The large magnitude means that it's highly thermodynamically favored. Ka-chow. To review, at constant temperature and pressure, a chemical system will proceed spontaneously in whichever direction lowers its free energy. At equilibrium, the system has the lowest total free energy available to it, so no further free energy change occurs. Delta G is equal to 0. So far, we focused on the free energy change at standard pressure and with standard states. So let's see if we can see how changing the pressure and/or concentration will influence spontaneity. Let's look at how pressure affects free energy. Recall that, by definition, Gibbs free energy will depend on enthalpy, temperature, and entropy. Enthalpy, for ideal gases, isn't influenced by pressure at all. And we've already looked at the dependence of free energy on temperature in the last video. So let's move on and look at entropy, S. Entropy does depend on pressure because of positional entropy and positional probability depending on the volume and space that particles occupy. Generally speaking, since pressure and volume for ideal gases are inversely related, the greater the pressure of the gas, the lower its volume, and the lower its positional entropy. Additionally, this relationship can be derived, probably somewhere in your textbook, where the Gibbs free energy is equal to the standard free energy plus the universal gas constant times temperature times the natural log of pressure. Don't worry about this derivation. Let's just see what we can do with it. If we do some algebraic manipulation, not shown here but probably shown somewhere in your textbook, throw in a dash of the law of mass action, and we'll ultimately end up with this relationship. This shows the relationship between the standard free energy change and the free energy change under non-standard conditions. Remember that Q is the reaction quotient, so the law of mass action applied to a system that may or may not be at equilibrium. And remember that T is the Kelvin temperature. For R, the universal gas constant, we'll need to use the 8.314 joules per Kelvin per mole, so that we'll end up with energy units. So let's practice using this equation with a sample problem. So one method for synthesizing methanol involves reacting carbon monoxide and hydrogen gases as shown here. Let's calculate the free energy change associated with this reaction at 25 degrees Celsius, but not under standard pressures, with 1 atmosphere of each gas, but instead with 5 atmospheres of carbon monoxide and 3 atmospheres of H2. We'll need to determine the standard free energy change, and we'll need to determine Q. For delta G naught, we can use the standard enthalpies of formation from the textbook Appendix and end up with a negative 29 kilojoules per mole of reaction. So we know that under standard conditions, this reaction is thermodynamically favored. Then to find Q, we'll find the reaction quotient is 1, all over the partial pressure of carbon monoxide times the partial pressure of hydrogen squared. Notice that methanol doesn't appear in the expression because it's a pure liquid. Its concentration doesn't change during the process. Anyway, so Q is 1 over the quantity 5 times 3 squared, which is 0.022. Now we plug everything into the equation for non-standard delta G, and we get negative 38 kilojoules per mole of reaction. This is significant. Notice that under these conditions of higher pressure of reactants, that the forward reaction is more thermodynamically favored. If we had applied Le Chatelier's principle to this system at equilibrium, we would have predicted exactly that. A shift to the right, favoring the forward reaction to get to equilibrium and achieve the lowest possible free energy state for the system. Neat! So, that a reaction is thermodynamically favored. So what? What does that result mean? Does it mean that mixing 1 mole of carbon monoxide gas and 2 moles of H2 gas together at pressures of 5 and 3 atmospheres will give us 1 mole of liquid methanol? No, it doesn't mean that. While it is true that 1 mole of liquid methanol has a lower free energy than 1 mole of carbon monoxide at 5 atmospheres and 2 moles of H2 at 3 atmospheres, there's an even lower free energy available to this system. And that state is equilibrium. Think of it this way, with a mechanical analogy of a ball rolling down a ramp. When the system proceeds from the reactants, point A, towards the products, point B, in the case of the reaction we're talking about here, point B has a lower free energy than point A. But point C is somewhere in between having just the reactants and having just the products. It's an equilibrium position, with the lowest possible free energy available for this reaction system. Hey, guess what we're going to talk about in the next video?